Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we have been studying polynomials over a field, and in the last, I have stated a very important theorem which says that the field of complex numbers is algebraically closed. So let us recall quickly what we did from the last time and continue from there. So we have defined the definition a field K is called algebraically closed if every non-constant polynomial f with coefficients in k has a 0 in k. Then we say the field is algebraically closed. In the notation, that is our notation V, K, F, this is the set of zeros of F in K, this is non-empty. So that means there is at least one zero of F in K. Or this is equivalently every non-constant polynomial f in K splits into linear factors. In Kx. So again in the notation, that is f will look like some constant a, x minus x1 power alpha 1, x minus xr power alpha r, with this a is a constant, non-zero constant, and x1 to xr, small x1 to xr are elements of K, they are distinct, and with their multiplicities are alpha 1 to alpha r, these are non-zero natural numbers. So in this case we actually know therefore what is V of f. So therefore Vk of f, actually we know it is the set x1 to xr. When you write in the set notation, we don't write the multiplicities. So this x1 is occurring alpha 1 times in f, x2 is occurring alpha 2 times in f, and so on. xr is appearing alpha r times in the linear factor, the multiplicity of xr. Also this finding out the multiplicities is also a task, but that is not so difficult like a factorization. So that when time comes, I will indicate some methods to do so. Another way of thinking is equivalently every prime polynomial in Kx is linear. That's all these conditions are equivalent is very easy to see, and after this we should see some examples of algebraically closed fields as well as algebraically non-closed fields. So therefore it is very important after every definition to give examples of that kind and of not of that kind. So some examples. So the first one of course is what I stated it as a theorem. This is a theorem of which we will prove. Theorem of Gauss, D'Alembert. Gauss was German and D'Alembert was French. And the theorem says that the field of complex numbers which we denote by this C with a double line is algebraically closed. I will just mention here proof later. Little bit history about the theorem. So we have a field which is algebraically closed, C. I want to give little history, not more, but it is very interesting. So first of all, formally stated by D'Alembert. (1746). Before that, the mathematicians they didn't find a need to prove this. They somehow calculating and they were convinced that the zeros of polynomial equations with real coefficients have complex zeros. But how did D'Alembert formulate it? Because he formulated this because he wanted to solve differential equations. And to solve the differential equations, if you know that, especially for the partial fractions occur there, and to do that you need a denominator polynomial should split into linear factors. And then there are standard techniques to integrate partial fractions, and that is what he wanted to do. And in that connection, he stated this formally and also offered a proof with proof. And what was his proof? I will just state it. He had two steps in the proof. Number one, the first step in the proof was, as I said in the last lecture also, you think of polynomials as polynomial functions. So we want to prove that if f is a non-constant polynomial in Cx, f non-constant, then we want to prove that f has a complex zero. So think of f as a function from C to C, any z going to f of z. And we want to prove that it has f has a complex zero means, so to prove for some z f of z becomes 0. F of z is 0 for some z in complex number. But this is equivalent to proving 0 is in the image of this function f. Image of f is by definition take all z and take their images in C. This is f of C. So this is what we want to prove. 0 belong to the image. Then there will be some z which will go to 0. That means what we prove it. So for this he claims two things. Number one, he claims, so no, this is not one. Number one, he claims that F is a closed map. Here I will use little bit terminology what one learns in a very first course on analysis. So closed map means the C has a metric space, C has a metric on that, and we talk about open subsets, closed subsets, etc. with respect to that metric. So closed map means F maps closed set to the closed sets. F maps F of any closed set G is closed for every closed subset G of C. That means F is a closed map. And the second claim he makes that it is F is an open map. That means F maps closed sets to the closed sets. And because of our assumption F is a non-constant polynomial, since F is non-constant, the map F from C to C is also non-constant. So we have a map from C to C which is open map and which is also closed map. And we learn again in the first course of analysis that if you have a map like this, so that means F of C, this is because C is closed in C, this is closed, and C is also open in C, so this is open. And because it is non-constant map, this is non-empty. So we have a non-empty subset which is both closed and open. And then one learns again in first course in analysis that then F of C must be C. This is, I would just say, analysis. In particular, 0 belongs to F of C. In particular, zero belong to F of C, which is what we wanted to prove. Now you see this proof is very good. The first part, closed map, also can be proved very easily. For doing that, one needs to use what is known as Hein-Borel theorem, which I am not going to elaborate on this because we are going to prove it in a different way anyway. And this proof was not accepted by mathematicians at that time because that F is open map. D'Alembert didn't state in this format. I am stating this format in the modern language, but that time this theorem which said that if you have an analytic function, then it is an open map. This was not non-constant analytic maps are open maps. This was not yet proved. This was finally proved by Gauss later. So this proof was not accepted that time, and this proof had considered gaps. So later on, the first person to give correct proof was Gauss. First correct proof. That was, I think, 1801. And there that happened because only after he proved open mapping theorem, maximum modulus theorem, and all those things, Liouville's theorem, and only then it became more and more clearer. Till then, this was not very clear. Also, a little word about this. Any proof will involve some analysis, that is unavoidable, but one can try to minimize the use of analysis. So this is what I will do it in when I give a formal proof of this theorem. That is because if you see, definition of complex numbers is complex numbers are constructed from real numbers. Real numbers are constructed from the rational numbers, and this here, this gap is big here. This construction of real numbers from rational numbers is only by limit, which is a concept in analysis. Here it is not too bad. Here it is an algebra construction. Before that also an algebra construction. But definition itself of C or R involves some kind of analysis. So that one cannot avoid to give any proof of fundamental theorem of algebra. And I will give a proof which is due to Lagrange after maybe 2 lectures. But before that, now I want to still discuss examples of, continue discussing examples of algebraically closed or non-algebraically closed. So far we have one example of algebraically closed field. The fields Q and R are not algebraically closed, not. Simply because you look at the polynomial x square plus 1. This is a polynomial with rational coefficients, and therefore we can think also polynomials in real coefficients, and there is no 0. Q of this polynomial is empty set. Also real zeros of this polynomial, there is nobody, therefore it is an empty set. Therefore this polynomial is non-constant, in fact degree 2, and has no real or rational zero. So these fields are not algebraically closed. So another set of examples, Z mod P, where P is a prime number, or for that matter any finite field F. I have not shown you that such fields exist, but we will also show in a due course later that how to construct more finite fields by using Z mod P. Z mod P is very easy to construct just from the congruence model of P. So these fields are not algebraically closed. So simply because now I have to produce you a polynomial which is a prime polynomial and which is not linear. If I do that, then it will not be algebraically closed field. But this also I will postpone it a little bit, because anyway I am going to discuss some properties of the polynomials, and from there it will become more and more clearer that these fields are not algebraically closed. We only have mentioned last time that the number of prime polynomials with coefficients in Z mod P are infinitely many. But we didn't say anything about the degree. Actually that also shows that, because if you have note that we have proved earlier, there are infinitely many prime polynomials in Z mod Px. We have noted this, infinitely many. That is the same proof as Euclid's theorem on the infiniteness of the prime numbers. But then how many linear polynomials are there? There are only finitely many linear polynomials, because linear polynomials looks like ax plus b and prime, therefore I could have even said monic. So the linear polynomials are these. So there are how many linear polynomials are there? As many as the coefficients b. But b can vary only in a finite field. So therefore there are finitely many. So there must be a prime polynomial which is of degree more than 1, and therefore finite fields are not algebraically closed. So now in former days, like Galois and even his predecessors, they were more concerned about the rational polynomials, and they were not concerned about over finite fields. Finite fields, in fact, were not clear that time. So I want to draw some consequences of fundamental theorem of algebra that is C is algebraically closed. From this I want to draw some consequences about rational polynomials and real polynomials. So the first I want to write that as a corollary. This corollary to the fundamental theorem of algebra. So the monic, I want to describe all monic polynomials in Rx. The monic prime polynomials. I don't have to say because we have made that convention monic. Prime polynomials in Rx are precisely they are linear ones, so they are like this x minus c as c varies in R. They are infinitely many. Or and x square plus px plus q with p, q real numbers and p squared minus 4q is negative. Note that in the school days you might have realized that this number becomes very important, that is called the discriminant of this polynomial. So I will just say discriminant of x square plus px plus q. In particular, if I prove this, then what would have noted? In particular, the prime factorization of arbitrary polynomial f in Rx, where f is non-zero, contains only linear and quadratic polynomials with this condition. Contains only linear and quadratic factors with negative discriminants. So that is already good information about real polynomials. Okay, so now let us spend a few sentences for the proof of this corollary. So proof. So we have given a non-zero real polynomial and we want to factorize, we want to find a prime factorization. And last time for arbitrary field we have noted that if I have a non-zero polynomial, then you take out the real zeros and they will correspond to the linear polynomials, and the remaining part is the prime polynomials of higher degree. And there I want to show now that higher degree parts are irreducible. So that means I only have to show that if f is a polynomial, non-zero polynomial of degree bigger equal to 3, then f is reducible. So it can't be prime then. So till the degree drops down to less equal to 2, and then we will worry about the discriminant condition. So I have to show this. If you have polynomial of degree bigger equal to 3, then it is reducible. That means it factorizes into Rx. So I will divide the proof in two parts. One, the degree is odd and the degree is even. Odd degree polynomial odd degree polynomial, if you try to draw graph of that function, polynomial function, then the odd degree polynomial, we know that the degree is odd, therefore it will look like x power 2n plus 1 plus lower degree terms. I could have also assumed it is monic because we only want to, so I could also assume monic. So when the x become very large, this is positive, and when it becomes very negative large, then it will go down to the, so the graph will look like something like this. So that means on the large side, large positive side, the value of this polynomial is positive, and large negative side value is negative, because the sign of the value is determined by the top degree term, and when x is negative, this is odd, therefore it is negative, this is positive. So that means, and f is a continuous function, polynomial functions are continuous, therefore it has to cross the real axis somewhere, and at least once. Therefore, wherever it crosses, those are the real zeros, but it is at least one. So that shows that in fact odd degree polynomial has a linear factor. So f has linear factor. In particular, it is not irreducible. In particular, that is reducible. Now the even degree term, if it is even degree, then note that because it has a real coefficients of f are real. So if, and we know by fundamental theorem by FTA, fundamental theorem of algebra, this polynomial f is in Rx, therefore it is contained in Cx, and therefore by fundamental theorem of algebra there exists z in complex numbers such that f of z is 0. But if f of z is 0, then f of z bar is also 0. But then what is f of z bar? That is, because f has a real coefficients, this is nothing but f of z bar. Because when you take the bar of the polynomial, that will go down to the bars of the coefficients and bars of the powers of z. That powers of z bar will be powers of, a bar of the powers of z will be powers of z bar. So then this equality is clear. So that means if f of z is 0, then f of z bar is also 0. So that means they appear in pair. So, and if z were a real number, we are happy, because then x minus z is a factor. And we know we get what we want. If z is not real, then z bar is also not real. And therefore these two linear factors of z, x minus z and x minus z bar, they are linear factors in Cx, and they are different because z and z bar are different. So therefore the product will also divide f. So then x minus z times x minus z bar, this divides f in Cx. But actually this is a real polynomial. You just have to write down the formula for that. So note that x minus z and x minus z bar, when you expand it, it is x square minus z plus z bar x plus z bar, but this is same as, this is the real part. So this is same as x square minus real part of z, and this is mod z square. So this actually has a real coefficients. So therefore this is a factor of f in Rx. So that means f is not that is f is therefore reducible. There is slightly one error which I would like to correct it. So for example, when I said look at the product x minus z times x minus z bar, this product is this line is okay. Here it is 2 times real part, and 2 times real part is also real number, and this is also real number. Both these are real numbers. So therefore, this is a factor of f in Rx. So that means the polynomial f is reducible, and that is what we wanted to conclude in the last part. So that proves that our claim that if you have a degree more than 3, then the real polynomial cannot be prime polynomial. Okay, we will continue after. So what we are doing is we are assuming that the assertion that the field of complex numbers is algebraically closed, and we want to draw some consequences about the polynomials and their zeros of in a field of rational or real numbers. I will continue this after the break also. Thank you.